review some of the material just discussed. The characteristics of an amplifier may be described in terms of a few basic parameters: gain, impedance, and distortion. As you recall, the gain of a circuit is a measure of the increase in signal level from the input to the output. The input and output impedance of an amplifier must be matched to the connecting circuits if good power transfer and low distortion are desired. There are three basic types of distortion which may occur in an amplifier circuit. These are frequency distortion, phase distortion, and amplitude distortion. The DC power supply used for an amplifier circuit must satisfy three requirements. It must supply sufficient energy to the amplifier stage, it is used to set the operating point of the device, and it is used to set the electrical operating conditions of the amplifier circuit. A family of characteristic curves may be plotted for any amplifier. Once the family of curves has been plotted, a DC load line may be drawn. Typical amplifier operation will usually be somewhere along the DC load line between saturation and cutoff. When no input signal is applied to the amplifier's operating conditions will be at a specific point on the DC load line. This point is referred to as the quiescent operating point, or simply the Q point. The quiescent operating point is set by three parameters: 1, the collector to emitter voltage; 2, the collector current; and 3, the base current. The Q point of a Class A amplifier will be located at the midpoint of the linear portion of the characteristic curve. The Q point of a Class B amplifier will be located at the cutoff point on the characteristic curve. And the Q point of a Class C amplifier will be located at approximately 2½ times the cutoff point. Class C amplifiers are never used for audio reproduction. This concludes our first review. As you learned earlier, the operating point of the amplifier is set by the bias circuitry. This will usually be a fixed current bias arrangement. The base bias current is determined by the VCC and the base bias resistor RB. The fixed bias circuit shown is quite simple, requiring a minimum number of components. However, in a practical circuit, the bias requirements of a circuit will change during normal circuit operation. As the ambient temperature changes, so will the biasing requirements of the transistor. This is due to the fact that as the temperature increases, the collector current through the transistor will also increase, so some other bias arrangement is generally preferred. The base bias arrangement shown here will provide some improvement over the previous fixed bias circuit. This circuit uses collector feedback bias to allow the base current to react to changes in collector current. As you notice, the base resistor is attached to the collector of the transistor and not to VCC. If the collector current increases for any reason, the collector voltage will decrease, which will cause the voltage being applied to the base of the transistor to decrease. This in turn will cause the transistor to conduct less current and stabilize the circuit. By using the collector feedback method, the base current can be controlled by the collector current of Q1. However, this does create a new problem. Since some of the circuit's AC output is fed back into the base of the amplifier during normal operation, it will reduce the gain of the amplifier. Even though the gain loss may be a disadvantage, the collector feedback bias is widely used because of its simplicity. Here we see a more commonly used bias circuit. The two resistors RB1 and RB2 form a voltage divider network which places a fixed voltage at the base of Q1. This voltage divider also places a fixed voltage drop across the emitter resistor RE, which in turn sets the emitter current at a constant level. Since most of the current which flows into the emitter will also flow through the collector, it ensures that the collector current will remain constant. the voltage drop developed across RB2 will equal the sum of the voltage drops across RE and the emitter base junction of Q1. The emitter base junction will normally have a 7/10 volt drop, therefore the voltage drop across RE will be 7/10 volt less than that of RB2. Care must be taken when choosing the values of RB1 and RB2 to ensure that changes in the transistor's base current do not affect the DC bias at the base. The current flow through RB1 will be the sum of the base current and the input current and the current flow through RB2. Remember, as the circuit amplifies the input signal, the base current must change. The base current, therefore, must be small when compared to the voltage divider current in order to prevent changes in the voltage drop developed across RB2. This is accomplished by choosing RB1 and RB2 values so that the voltage divider current will approximately equal the collector current of the circuit's Q point. Since most small signal amplifiers have a current gain of 20 or more, the base current will be 1/20th or less than the collector current flowing through the transistor. Therefore, this small base current will have little effect on the base voltage. The stability produced by the voltage divider bias circuit makes it a very popular design for amplifier biasing. Semiconductor devices used in power amplifiers differ from those used in voltage amplifiers both physically and electrically. This is because power amplifying devices are physically larger and are designed to operate with higher voltage and current levels than those required for the smaller signal amplifiers. Other than this, the basic concept of both types of amplifier circuits are quite similar. When working with amplifier circuits, the DC power supply must satisfy three requirements. It must supply sufficient energy to the amplifier stage. It is used to set the operating point of the device for proper operation. And it is used to set the electrical operating conditions of the amplifier. The DC circuit used to set the operating conditions of the amplifier is referred to as the bias circuit. The bias circuit should prevent changes in the operating conditions even if the amplifying device's characteristics change during normal circuit operations. A well-designed circuit will provide for a stable circuit operation. The load resistor, RL, which is attached to the output of the amplifier along with the power supply, is used to set the power output limitations of the amplifier. The output signal current cannot exceed the power supply voltage divided by the load resistor. This can be better illustrated using a simple transistor circuit. As you can see, the maximum current flow through the transistor is limited by the load resistor RL. When the current flow through the transistor is stopped, the voltage drop across the emitter collector of the transistor will equal the power supply voltage. Between the saturation and cutoff limitations of the transistor, there are an infinite number of current levels. Therefore, the current flowing in the output circuit at any instant must be between these two limits. Here we see a typical common emitter family of characteristic curves. At point A, we see that the transistor will conduct a little over 3 milliamps of current and develop a 10-volt drop across the collector emitter of the transistor with a 20 microamp bias current being applied at the base. By using Ohm's law, R equals E over I, we see that the transistor is developing a resistance of approximately 3,226 ohms. If the voltage drop across the transistor is held constant and the base current is increased to 50 microamps, we see that the collector current will increase. For this to happen, the transistor's emitter to collector resistance had to decrease when the base current was increased. By knowing the maximum collector current and the maximum collector emitter voltage drop, a DC load line can be drawn. The maximum collector current is developed when the transistor is at its saturation point, and the maximum collector emitter voltage drop occurs when the transistor is at its cutoff point. Typical amplifier operation will usually be somewhere along the DC load line between saturation and cutoff. When no input signal is applied, the amplifier's operating condition will be at a specific point on the DC load line called the quiescent operating point, or simply its Q point. The Q point is set by three parameters. First, the collector to emitter voltage, the collector current, and the base current. When the input signal is applied at the base current will change, and this will result in the other two parameters changing along the DC load line. When the base current increases, the parameter will shift up the DC load line. And when the base current decreases, the other two parameters will shift down the DC load line. Small signal amplifiers are designed to increase the amplitude of the incoming signal. To allow for the widest variations in amplitude, the Q point should be located at the midpoint of the DC load line. This allows the signal to fluctuate the maximum amount between these two extremes. Here we see another graph representing a characteristic curve of an amplifier between cutoff and saturation. Notice that the quiescent operating point, or Q point, is located at the midpoint of the linear portion of the curve. If the input signal is not too great, the circuit will operate in a linear mode and negligible amplitude distortion will occur. This is the operating point of a Class A amplifier. Power amplifiers, on the other hand, are usually operated as Class B amplifiers and are biased at the cutoff point on the curve. This allows only the increase of base current to become amplified. Since part of the signal is amplified in the lower knee of the curve, it will produce some distortion. Generally, power amplifiers are operated in the push-pull configuration. This allows for proper amplification of both sides of the signal. Another type of power amplifier is the Class C amplifier. The Class C amplifier is normally biased at 2.5 times the cutoff point. Obviously, the Class C amplifier introduces significant amounts of amplitude distortion and is not used for audio reproduction. Notice that Q1 only produces pulses of current into the tank circuit. Since Q1 does not continuously conduct a steady flow of current, it cannot faithfully reproduce the incoming signal. Class C amplifiers are normally used in oscillator circuits. Another class of amplifier operation is the Class AB1 and Class AB2. As you recall, the Class A amplifier was biased at the center of the linear portion of the characteristic curve, and this resulted in lower distortion. The Class B amplifier, on the other hand, was biased at the cutoff point on the curve, which resulted in a more efficient circuit, but also some distortion. It is possible to bias two transistors in a push-pull configuration somewhere between the Class A and Class B bias points. These amplifiers are called AB amplifiers. The Class AB amplifier is less efficient than the Class B and more efficient than the Class A amplifier. At the same time, they have less distortion than Class B amplifiers and more distortion than Class A amplifiers. There are two types of AB amplifiers, AB1 and AB2. The Class AB1 amplifier is biased a little more negative than the Class A operating point. In the Class AB2 amplifier, its operating point is biased even further negative than is the AB1. Normally, the AB2 bias point will be at the top of the lower knee of the characteristic curve. Since the AB2 is biased more negative than the AB1 operation, it requires more driving power than the AB1 amplifier.